Okay, so it's Thursday, April 30th, and we're here working on general chemistry, section 16.3, which is, or sorry, 16.4, which is acid-base properties of salt solutions. Okay, so we've seen equilibrium situations with weak acids and equilibrium situations with weak bases. Now, how about with a salt solution? Okay, well, with a salt, we have to take a look at, we'll just use the example out of the book. If we put this salt into water, okay, it's going to dissociate. Remember our solubility rule, sodium is always soluble. So we're going to get two ions in solution. Okay, now how do we determine whether this solution is going to be acidic or basic? Well, we're going to take a look at how each of these reacts with water. Okay, now we know that sodium cation comes from the ionization of a strong base. So this plus water is going to give us no reaction. Because remember, this came from sodium hydroxide dissolving in water, which gave us this plus hydroxide anion. Now, if this were going to react with water, it would reform sodium hydroxide. All right, it would pull a hydroxide off of the water and reform this. But we know that doesn't happen because as soon as this would form, this is a strong base, as soon as it forms, it would go back this way. We conclude this reaction does not happen, right? It does not happen, right? So how about the cyanide ion? Well, where does that come from? Well, that comes about from the dissociation of the weak acid. Sorry, we should put plus water. From the dissociation of this weak acid. So we're going to get hydronium ion plus cyanide. Okay, now cyanide is the conjugate base of this weak acid. This can, in fact, react with water because this reaction can go in this direction here. So I can have cyanide reacting with water to give me the reform HCN, okay, plus what's going to be left of the water, hydroxide anion. So this reaction on the bottom is called a hydrolysis reaction, right? Hydrolysis generally means something's reacting directly with water, right? So the cyanide ion is being hydrolyzed by water. The cyanide pulls an H plus proton off of the water molecule, reforms the weak acid, leaving us with a hydroxide anion. So that means that this solution here, or this reaction does occur, and the solution will be basic because it produces hydroxide anion. This reaction does not happen to any major degree, but nonetheless, we're just looking in the solution, there will be at least a slight excess of hydroxide anion. So we can conclude that this up here, this salt, when it dissolves in water, will produce a slightly basic solution, right? So probably somewhere around pH 8, pH 9, somewhere around there, depending on the concentration of the sodium cyanide salt. Okay, any question there? So again, so we conclude that when we have a salt of a strong base and a weak acid, we're going to get a slightly basic solution. Okay, let's look at the opposite effects. And just, any question or comment there? How about if we have a salt from, let's say, well, do they have an example in the book? Yes, they do. So suppose we had something like, or sorry, NH4Cl. And this is going to dissolve in water to give us NH4 plus Cl minus. Okay? So we want to determine, will the pH of this solution be acidic or basic? Well, let's take a look at what's going to happen here. Okay, and let's go back to the red for that. So this is the conjugate acid of a weak base, ammonia. Can this react with water? And the answer to that is yes, it can. It can give me, this is an equilibrium situation, that can give me ammonia molecule plus hydronium cation. All right, so that's going to be slightly acidic. Slightly acidic. How about the chloride? Can that react with water? Well, remember that chloride comes about from the dissolution of hydrochloric acid, which is a strong acid, completely ionizes to give me H3O plus Cl minus. Okay, so that's where this is the anion of a strong acid. It will not react with water. In other words, this reaction will not work. This reaction will not work because as soon as the HCl is formed, it's immediately going to dissociate. So this reaction is never going to happen, right? So we're never going to get any of this reaction to occur. We will get this reaction to occur, which produces hydronium ion, So that means the pH of this solution, ammonium chloride, will be slightly acidic. Slightly acidic. It's not going to be like pH 1 or 2. That's strongly acidic. It'll be around maybe pH 5 or 6, somewhere around there. Like once again, depending on the concentration of the solution. We're going to calculate pHs of salt solutions here in a few minutes. All right? But right now, it's good enough for us just to recognize that the ionization of a salt from a cation from a weak base and an anion from a strong acid will produce a slightly acidic solution. Okay? Any questions or comments there? Any questions or comments? Well, let's look at a different one. And I believe this one is in our book also, but let's take a look at sodium chloride. All right, well, that's going to give us sodium cation plus chloride anion. But we just saw that this does not react with water and this does not react with water. Right? We just proved that in both cases here. That this is the cation of a strong base, this is the anion of a strong acid. Neither of them react with water, so we should expect this a solution of sodium chloride to be neither acidic or basic. So we should expect the pH of any sodium chloride solution to be right around 7.0, assuming there's no other chemicals in the water. Okay? Any question here? Now, I just want to point out to you, you have to memorize, well, let's see, that ammonium chloride one gave me, well, that was, okay, the cation, the conjugate acid of a weak base gives me an acidic solution. You have to memorize that. No, you don't. You should be able to just write it out just like we did. Just write it out. Take the cation, react it with water. Does anything happen? Take the anion, react it with water. Does anything happen? Okay? Now, you are going to have to keep in mind, back in the last chapter, we had that little table of strong acids and strong bases. So you're going to have to reflect back to that because you probably don't have enough experience to know necessarily that bromide anion is the conjugate base of a strong acid. You're going to have to probably refer back to that table to look. All right? Okay. I forget what page it was on, but it's back here in chapter 15. All right. So let's take a look at We have this little table in green, but it's kind of what we just did here. Let's take a look at the fourth one. What if you have something like we forgot the case of something ammonium, and let's just use the example that they have in the book. I think they use formate. I'm going to use this one. All right. I don't like the way our book writes formate. So this is going to give us NH4 plus NO2 minus. Now, this is the conjugate acid of a weak base, ammonium, NH3. This is the conjugate base of a weak acid, HNO2. Right? So now they're both weak. What do we do here? Because we should expect, since they both come from weak, this comes from weak base, this came from a weak acid, we should expect each of these ions to react with water. And in fact, that's exactly what happens. We already know the ammonium does. NH4 plus water gives me NH3 plus hydronium ions. All right? So we should expect this solution to be slightly acidic from this reaction. But in this case, we have the conjugate base of a weak acid. So that's going to react with water also. NO2 minus plus H2O gives us HNO3. So we get the weak acid back plus hydroxide ion. Okay? Now, one of them produces hydronium ion, one produces hydroxide ion. So what's the pH? Is it going to be acidic or basic? And as our book tells us, you're going to have to look at this on a case-by-case basis. You can't give a hard and fast rule for this. It's going to depend on what the Ka values are and the Kb value is for the ionization of the weak acid and the weak base. But again, you're going to have to look at it on a case-by-case basis. Okay? All right, so let's take a look at, I usually don't do the examples, but let's go ahead and do that for this one. So we don't have to work out a long problem here. So example 16.6a. So we just want to predict whether these solutions are acidic or basic. And the first one is potassium chloride. Well, that's going to give me, when it dissolves in water, potassium cation and chloride anion. So we want to look, does either of these react with water? This came from KOH dissolving in water. So it is the conjugate acid of a strong base. So this is extremely weak acid, extremely weak. It's not going to react with water. Not going to react with water. We just saw that this is the conjugate base of a strong acid, HCl. It is not going to react with water either. It's not going to react with water either, so we should expect the pH of this to be neutral. Expect the pH to be neutral, which is exactly what our book tells us. Okay, any question here? Any question? Remember, the alkali metal hydroxides are all strong bases. They're all strong bases. Right, so that's how I knew that this is the conjugate acid of a strong base. All right, let's look at B, the next one. And then we'll do the exercise also. So sodium fluoride. All right, so we put that in the solution. We get sodium cation and fluoride anion. Well, we already know that the sodium does not react, right? Because that came from, this is the conjugate acid of a strong base. So this does not react with water. How about the fluoride anion? That came about from this, HF plus H2O gives us, this is a weak acid, so it's going to give us H3O plus F minus, right? This is a weak acid, so we should expect this, the conjugate base, to react with water. So let's take a look at that. F minus plus H2O gives us, this will be an equilibrium situation, it's going to reform the weak acid plus hydroxide, right? So the sodium does not react with water at all. The only contribution as far as acidity or basicity is from the hydrolysis of fluoride anion. Again, hydrolysis is just something reacting with water. It's going to form the free acid and give us hydroxide anion back. So we should expect that solution to be at least slightly basic. Slightly basic. Okay, any questions or comments? All right, let's look at part C, which is, oh, we forgot to do the complex ions. We'll take a look at one here. I skipped over that one. I forgot about that. So the zinc nitrate. All right, and we put this into solution, and we're going to get zinc 2 plus 2 nitrate anions. Okay, now this is the conjugate base of a strong acid, HNO3. Right? This is a strong acid. It reacts with water. It's a one-way street to give us hydronium ion plus nitrate anion. So this does not react with water. Right? So the solution, the reaction only goes in that direction. So this is not going to react at all. How about the zinc? How about the zinc? And again, you can look back in the chapter 15 and we see that this is a strong acid. So nitric acid, HNO3, is a strong acid. HNO2, which we saw in a problem before, is a weak acid. How about zinc? All right, well, zinc forms in water one of these complex ions. All right, so we kind of saw these last week when we talked about the Chatayer's principle lab. Okay, and if you want, you can turn to the previous page here. On page 559, they talk about the complex ion formation of zinc. Now, what can happen here? Okay, one, the zinc is it can pull actually the zinc is positive. So when the complex ion forms, the negative ends of the water molecules point towards the zinc. Right, so the negative ends of the water molecules are pointing towards the zinc here. And let's see here. Now, so that means the electrons are being pulled away from the protons on the water molecules, right? So the protons become acidic because, again, all the oxygens are pointing towards the positive zinc. So one of these water molecules can lose a proton. Here, actually, maybe we should write it out like this. I'm going to run out of room here. Plus water, all right, is going to give us Zn H2O 5, and then OH minus, then the hydroxide. And so we started out with the zinc plus 2, One of the water molecules has lost a proton, so now the charge is just +1. Now the charge is just +1. What happened to, so this water molecule became protonated from one of these 6. You see, we started out with 6 waters, now we have 5. What happened to that 6th water? Well, it split into H+, which protonated this, so I'm going to get, this is going to become H3O+. And then where's the OH? The OH is still a ligand on the zinc cation, right? So we still have 6 ligands on the zinc, but now it's 5 waters and 1 hydroxide. We started out with 6 waters. So this solution will be slightly acidic, okay? And again, if we look on the previous page, I won't write it on the board, okay? But they give the example. Let's go over that with the aluminum, since I forgot about that. The aluminum is the exact same reaction. The aluminum starts out with a charge of +3 with 6 water ligands. Okay, it reacts with a solvent water molecule. It reacts with a solvent water molecule. One of the water molecules that functions as a ligand bonded to the aluminum releases a proton and protonates that solvent water molecule, the H2O liquid. So the H2O liquid becomes H3O+, and here we have the new aluminum complex ion. Aluminum complex with 5 water molecules, just like the zinc, and a single hydroxide. But notice the charge on the newly formed aluminum complex ion is not +3, it's +2, because this OH is negatively charged. This OH is negatively charged. The aluminum was +3, the OH minus add up to a charge of +2. Just like here with the zinc. The zinc is +2, but now it's complex with an OH minus. So that reduces the charge from +2 to +1. Okay? And again, this is all because all these water molecules are pointing, the zinc is positive. Remember, the water is highly polar. The oxygen end of the water molecule is positive. The hydrogen end, is negative. The hydrogen end of the water molecule is positive. So when this complex ion forms, all the water molecules orient themselves so that their oxygen ends are pointing towards the zinc. That's pulling electrons away from the protons, enough that one of them can be pulled away by a solvent water molecule. Okay, so that gives us the C there. All right, any question or comment on that? This one can be a little confusing. All right, that's any question or comment? All right, let's look at the 4th one, which, if I remember correctly, is the salt of a weak acid and a weak base. All right, so let's look at that one, which is ammonium cyanide. All right, so that's going to give us ammonium cation and cyanide anion. And we know that each of these, since this came about from protonation of, this is the conjugate acid of a weak base, ammonia, it can therefore react with water to give us neutral ammonia plus hydronium ion. Similarly, this is the conjugate base of a weak acid, so it will react with water. To give us the free acid back plus hydroxide anion. So the question is that we're getting both hydronium, which is acidic, and hydroxide, which is basic. What's the solution going to be? Well, we have to look at the Ka and the Kb here and we see here, let's see, they tell us here, rather than look it up, they just give it to us. The Ka for NH4 plus is 5.6 times 10 to the negative 10th, and the Kb for cyanide ion is 2 times 10 to the negative 5th. right? So this one is occurring fivefold greater than this one. Again, let's write the K, Ka, and Kb up here. I'll write it in green. Right? This one is 10 to the negative 10th. This one is 10 to the negative 5th. So this one is occurring 100,000 times greater than this one is. So we should expect this solution to be basic, right? We should expect it to be basic. The base concentration will overwhelm the concentration of hydronium ion from this hydrolysis reaction. Okay, any question there? Any question? We should have one. Okay. Where do we get the Ka for this reaction? Where do we get the Kb for this reaction? Because in our tables of Ka and Kbs earlier in this chapter, okay, there was a table for Ka of weak acids and a table for Kb of weak bases. But they were all neutral molecules. These are not neutral, they're charged chemical species. So how do we get this Ka of 10 to the minus 10 and this Kb of 10 to the minus 5th? We're going to see that in the next section or two, where those numbers come from. All right? There's a very simple yet powerful relationship that will allow us to calculate Kas and Kbs for charged chemical species. Okay? Because you can't really measure them. All right. So, actually, while we're still on this, let's do that exercise. Oh, geez. I'm trying to keep my book pristine. It's never going to happen. Well, I folded all the pages there. All right. Yeah, geez. All right, let's do the exercise that accompanied this. Now that we somewhat know how to do this, we'll do it a little faster. All right. So I think it was KNO3. KNO3. All right, so that gives us K plus and nitrate anion. This came from KOH, which is a strong base, so this is not going to react with water. This came from nitric acid, which is a strong acid, so that's not going to react with water. So this solution, a solution of potassium nitrate, we should expect it to have a neutral pH, regardless of concentration. Okay, how about B? That was B. That was B.
Yeah.
Let's look at A, which is ammonium nitrate. Ammonium nitrate. Well, we already know the nitrate's not going to do anything. Okay? And like I said, you shouldn't have to memorize these things. I don't memorize it. I just write it out and figure it out. Okay. Now, I know that's from the conjugate base of a strong acid, not going to react. This is the conjugate acid of a weak base, ammonia. So this will react with water. It can, in fact, be hydrolyzed by solvent water molecules. Give us neutral ammonia molecule plus H3O plus. So we should expect this solution to be at least slightly acidic due to hydrolysis of ammonium cation leading to hydronium ion. So we should expect at least a weakly acidic solution. All right, how about the next one? Let's see, aluminum nitrate. Aluminum nitrate. That's going to give us aluminum cation plus 3 nitrates. All right, but this is the conjugate base of a strong acid. Nothing happens. Will not react with water. All right, and what about the aluminum? Well, we already know that's going to form a complex ion in solution. right? So the aluminum accommodates 6 water ligands, all right? But as we just saw a moment ago, all right, these water molecules, as we just saw a moment ago, one of these water molecules in the complex ion can in fact react with a solvent water molecule. So I'll put L for liquid here, all right, to give us Al H2O 5 OH. All right, so one of the protons is pulled off of one of the ligand water molecules, turning it into hydroxide ion. So that's going to reduce the charge here from 3 plus to 2 plus, I've run out of room here. Where did that proton go that got pulled off of the water ligand? It goes to protonate one of the solvent water molecules, H3O plus. Okay, so we should expect the solution to be at least slightly acidic. Okay, and then the last one there, I'm not going to work that one out because we don't yet know how to calculate the Ka and the Kb. Oh, there's only 3 of them. We're done. Okay, any questions or comments? I see why they didn't put one with the conjugate acid of a weak base and the conjugate base of a weak acid, because you have to know how to calculate the Ka and the Kb for those, which we don't know how to do, which they're going to show us how to do right now in the next section. All right, so let's have a look at this. All right, let's go back to our HCN, or sorry, what's it? Sodium Okay, so let's take a look at this. This is a weak acid. All right, and now this, let's write a Ka for this reaction here. All right, so there's Ka for that. Okay, but now we know that this can be hydrolyzed by water. Give us HCN plus OH minus. Okay, let's write a KB for this, a KB. So KB equals products over reactants. Okay, now what we want to do here is I'm going to multiply. Notice that this reaction here is the hydrolysis of the conjugate base of this weak acid. All right? So what we're going to do here down here in green is I'm going to multiply Ka times Kb. All right? So let's go ahead and do that. So here, I'm going to put the Ka in black to make it stand out. So H3O plus times Cn minus divided by the free acid, HCN. Can everybody see that on the bottom? Yeah, you should be able to see that. Okay, then in red, I'm going to put the Kb. All right, and that is HCN times the molar concentration of OH minus divided by the molar concentration of cyanide, the conjugate base. Okay. Now, we'll give you a chance to write all that out. So our book is, if I remember correctly, is just skipping these two steps. They just give you the result. Okay, because we did do it earlier in this chapter. Now, we can cancel a bunch of stuff here. Here I have HCN in the denominator. Here I have HCN in the numerator. So I can go ahead and cancel those. All right, does everybody have this written down? Because I'm going to erase these rather than draw through them. So I can cancel that with that. Here I have cyanide anion in the numerator and cyanide anion in the denominator. I can go ahead and cancel those two. And lo and behold, what am I left with? Hydronium ion times hydroxide. Okay? And that is just equal to K, our old friend, Kw, the ionization constant for water, 1 times 10 to the negative 14th. 1 times 10 to the negative 14th. Okay? So what we have proven here is that if you take the equilibrium constant, the ionization constant for an acid dissociation, and the equilibrium constant for the hydrolysis of the corresponding base, you multiply those two together, you get a result equal to 10 to the negative 14th, right? Because you can't really measure this. This is going to be kind of hard to do, to measure this equilibrium constant. You can quickly calculate it. You can quickly calculate it. And certainly the equilibrium constant, Kas, for all these weak acids are tabulated. You can find them in some table. Our book has a table of them in the appendices. There's a much longer version of this. Okay. Similarly, if we could write this out for a weak base also, we could do this for ammonia, and it would be the same thing. Kb would be the base equilibrium constant for ammonia, and this would be for the hydrolysis of ammonium cation. All right, so we could get the Ka or the Kb in either event. So if we look back on page 360, or sorry, page 560, all right, this is how, if you look at number 4, okay, up at top in the green, right, when they were talking about how to predict whether a salt solution is going to be acidic or basic, right? In number 4, it says a salt of a weak base and a weak acid, where both ions hydrolyze. So you need the Ka for hydrolysis of the weak base, and the Kb for the hydrolysis of the weak acid, or sorry, of the conjugate base of the weak acid. Where do you get those? And they just gave you the numbers in that problem, right? This was how they got them. This, using this method right here, Ka times. So for here, let's look. Where did they get the Ka for NH4 plus? Let's look at that. Where did they get the Ka for NH4 plus? All right. Well, all right, so we wanted a Ka for this. All right, now again, you don't have it, but you know KB for this. So we can calculate KB equals KW Ka. This is an acid dissociation constant, divided by the KB for ammonia here. Divided by the KB for ammonia equals the Ka for the ionization of NH4 plus, ammonium cation. Okay, so you just look for the conjugate partner. Okay, the neutral species will have its value tabulated somewhere. Will have its value tabulated somewhere, and then you can just go ahead and calculate either the Ka or the Kb as specified for that particular problem. Do we have any questions or comments here? Any questions or comments? Okay, we'll do some problems here then. And the first couple, if I remember correctly, are quite easy. It's just calculating the Ka or Kb. Okay. All right, so I'm not going to do the example. Let's do the exercise. So 16.8, we want to calculate Kb for F minus. All right, calculate the Kb for F minus. In other words, right? So we want the Kb for this. Well, we don't know what it is. All right, however, we can look at this, the conjugate partner. And we can write HF plus H2O gives me, it's a weak acid, gives me hydronium ion plus F minus. Now I do know the Ka for this. I can look that up. Ka equals, so we go back to our tabulated set of Kas for weak acids, which is on page 547. And we see for a hydrofluoric acid, this is 6.8 times 10 to the negative fourth. All right, so now I can easily calculate Kb here. Kb is equal to Kw divided by Ka, which is equal to 10 to the negative 14 divided by 6.8 times 10 to the negative fourth. And we just get out our calculator. And so 1 E14 negative divided by 6.8 E4 negative equals, and I get 1.5 times 10 to the negative 11. So we can see this hydrolysis reaction does not happen to any major degree, right? It does not happen. The hydrolysis is happening 7 powers of 10. That's 10 million times less than this reaction here is occurring. 10 million times less. Okay, this is why we use logarithmic scale for pH and pOH. Any question here? Any question? All right, let's see, what time we at here? 4:53. I'm not going to do part B here. It's the same as this. I want to move on to actually calculating calculating the pH of one of these salt solutions. Calculating the pH. So this will take a little bit of time. We got to set up an ice table. Okay. All right, so we're asked. So benzoic acid and its salts are used as food preservatives. You can almost pick up any food, any perishable food in a grocery store without looking at the ingredients and seeing sodium benzoate listed as a preservative. All right, so we're asked, what is the concentration of benzoic acid in a solution of 0.015 molar sodium benzoate. Okay, now, so I get sodium benzoate, sorry, C6H, yeah, okay, I'm gonna write, we'll write, I hate writing acids the way they do in the book. All right, sodium H5O2. So there's the salt. I put it into water, it's going to become this. Right? Cation and anion. Now again, this is the conjugate acid, or this comes from dissociation of a strong base. So it's the conjugate acid of a strong base. It does not react with water. This is the conjugate base of a weak acid. It will react with water. It's capable of being hydrolyzed by water. So I'm going to write that on top up here. You should skip a line here. All right. I'm going to write this up here for this hydrolysis reaction and then erase this. Then we're going to make an ice table. All right. So C7H5O2 negative plus water gives us, right, the free acid back, HC7H5O2 plus OH minus. OH minus. Okay, now again, the hydrolysis of the base of a weak acid should produce a basic solution. So when we calculate that final pH, it better be above 7. All right, so now I'm going to erase this. I just wrote this out so we can see where this benzoate anion comes from. All right, so now we're going to set up an ice table. Ice, and the initial here I think was 0.015. Yeah, 0.015, 0, 0. Okay, and what's the change? Minus X plus X plus X. Okay, again, that comes from all the coefficients are 1. So every time this gets hydrolyzed, I produce 1 benzoic acid and 1 hydroxide. That's why these X's are all 1s. All right, and at equilibrium, I'm going to have 0.015 minus X plus X plus X. All right, so there's my ice table. All right, there's my ice table. All right, so now we want to set up KB here, an expression for KB. All right, let's see here. So I'm going to go ahead and do that. Remember that X is equal to the concentration of both the benzoic acid and the hydroxide ion concentration. All right, so we're asked to calculate what this X is, the concentration of benzoic acid. I'm going to erase this ice table. Actually, I guess I could have left it up and just used the other board. All right, so let's set up an expression for KB here. KB is equal to HC7H5O2 times hydroxide ion concentration divided by the concentration of benzoate anion. Okay, so I can plug in the values from my ice table. Okay, let's see now. We want to know if we can drop this X here. We want to know if we can drop this X. So in other words, and to do that, we need to know the value for KB, because what's going to justify us in dropping this X and avoiding a quadratic equation is, remember that little test we can do. So CB divided by KB, if that's bigger than 100, we can drop that X. Well, we know what CB is. It's 0.015. But what's KB? Well, we just learned a moment ago how to calculate KB. All right? So I'm going to do that off to the side here in black. All right? KB is equal to KW divided by Ka for benzoic acid. And they give us the ionization constant for benzoic acid. So this is equal to 10 to the negative 14 divided by 6.3 times 10 to the negative, what is it, 5? Yes.
It's 0.15 or 0.015. The CB, is it 0.15 or 0.015?
Oh, yes, 0.015. Yes, thank you. Thanks for catching that. Okay, so we divide these two. 1 times 10 to the 14th negative divided by 6.3 times 10 to the 5th negative equals 1.6 times 10 to the negative 20th. That's not right. I don't think I put the negative sign in on that. Do it again. What the heck? Okay, this should be negative 10. Okay, so that's the value for KB. So I'm going to bring that back over here. So CB is 0.015, KB is 1.6 times 10 to the negative 5th, or sorry, 10 to the negative 10. And get out the calculator. I still have this in my memory. I'm going to leave it in my memory because I'm going to need it later anyway. 0.015 divided by recall 1 equals, and it's enormous, 9.45. 9.45 times 10 to the 7th. So that's way bigger than 100. Way, way bigger than 100. Okay? Everybody have this? Everybody have this? All right, so we're justified in dropping this X. We're justified in dropping that. You see how all these things tie together? So I'm going to go ahead and I'm going to write, instead of an equal sign, I'm going to write KB is approximately X squared divided by 0.015. Okay? Or X is approximately, X squared is, yeah, we'll leave it like that. 0.015 times KB. All right, or X is approximately equal to the square root of 0.015 times KB. All right, and we'll bring that up here. So let's go ahead and plug the numbers in. X is approximately the square root and 0.015 and KB was, I have it in my memory here, 1.6 times 10 to the negative 10. All right, and that's approximately I get 1.5. I'm going to go with another decimal place. times 10 to the negative 6 molar. 1.54 times 10 to the negative 6 molar. So we've answered the first question. Let's see if that's okay. That's the concentration of hydroxide ion. Remember looking back at our ice table. It's the concentration. X was the concentration of both the benzoic acid, so we've answered that question. Right? We were asked to find two things: the concentration of the benzoic acid, the HC7H5O2, so we've answered that, and it's also the concentration of hydroxide ion. But we weren't asked to find the concentration of hydroxide ion, we're asked to find the pH. Okay, do we have any questions on this? Because I'm gonna erase this. Any questions? Nobody has any questions. All right, so here goes. I'm gonna put that in my memory. Store 2. All right. Well, I'm gonna try something a little different here. I know that POH is equal to negative log of OH minus. Is equal to negative log of 1.54 times 10 to the negative 6 is equal to, so log negative 5.81. So that's the POH. pH is equal to 14 minus POH. Remember, pH plus POH has to equal 14. So pH is equal to 14 minus 5.81, which is equal to 8.2, or 8.19. There we go. $8.19. I'm going to sit down here for a minute. Now notice, again, we tied a lot of things together here. All right, we use the ice tables. Now let me sit down here. All right, so we used equilibrium constants from chapter 14. All right, we used pH and POH scale from chapter 15. We used ice tables from this earlier in this chapter, chapter 16. We used what happens in a salt solution, the pH of a salt solution. We use that. We use that Ka times Kb equals the ionization constant of water, which comes about from the pH of a salt solution. So we used all these different things were tied together to solve this one problem. Okay, but it's really not that difficult. It really isn't. Okay, do we have any questions here? Let's see. No questions or comments. All right, let's do the concept check here, and then I think we'll be done here. All right, the concept check. All right. Notice there's a lot of places you can make a mistake here. You really got to be focused. Okay, when you're working these problems, you can't be like, you know, have the TV on and fighting with your mother or whatever. Right? You got to be focused. There's a lot of steps. Any one of them, you can make a silly mistake. You saw me make one. Somebody there corrected me where I wrote down the concentration of the sodium benzoate is 0.15 instead of 0.015. Okay, so let's do the concept check. We're given 4 solutions, all with the same concentration. All right, so the first one is, I'm not going to write down the concentrations because they're all the same. So NH3, ammonium bromide, actually I'm going to write them down on this little one. And then use the big one for, so NH3, NH4Br, and we have sodium fluoride, and sodium chloride. Okay? And we're supposed to rank them according to pH. Okay? Rank them according to pH. Now, the first thing I notice, there's no acids here, right? I have a salt, a salt, a salt, and a base, a weak base, right? Remember, these nitrogen-containing compounds are weak bases, right? So a salt, so here, let's write those down. A salt, 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 and a weak base. And remember, a salt is just any ionic compound, okay? Now, I do have a weak base. So this solution I expect to be the most basic. So this is the highest pH, all right? All right, so highest pH. Let's write that in green. Okay? Remember, from 7 to 14 is basic, 0 to 7 is acidic. So the higher the pH, the more basic. So this has the highest pH. Now, let's look at our salts. All right, let's look at our salts. Well, this is from, sodium is from, let's write it in purple here. The sodium is from a strong base. All right, the cation from a strong base, and the anion from a strong acid. So strong base, here, let's do it this way. Strong base and strong acid. So neither of those, the sodium or the chloride, is going to react with water. So I should expect a neutral pH there. A neutral pH. Maybe I should have written this on the big one. All right? So this is going to have a neutral pH, pH 7. All right? Now, let's look at the other two. This is the conjugate acid of a weak base. And this is the conjugate base of a strong acid. HBr is a strong acid. So that's not going to react with water. This will. This will. And finally, let's look at the sodium fluoride in our toothpaste. So this is from a strong base. And fluoride anion, F minus, is the conjugate base of a weak acid. It's from a weak acid. All right? So this is not going to react with water. All right? So we know this is not going to react with water. All right? So one of these two is going to give an acidic solution. So let's write out the hydrolysis reactions. All right? Let's write out the hydrolysis reaction for the weak base, NH4 plus H2O gives me NH3 plus H3O plus. All right, so that one's going to be acidic. Let's look at this one. F minus plus H2O gives me HF plus OH minus. So this one is going to be basic. All right, so the lowest pH is going to be this one. All right, so if we were to rank them by pH, the highest pH would be the NH3, highest pH. And then this guy, the sodium fluoride, is weakly basic, weakly basic. The NH4Br is weakly acidic. Oh, sorry, we should put the sodium chloride in there. That's neutral. And the NH4, sorry, the HF no, NH4Br is weakly acidic. So basic, weakly basic, neutral, and weakly acidic. You see how we can figure that out? See how we can figure that out. Okay, it's not that hard. All right, so we're at 5:15 here. Nobody had any questions today. The only time I heard anything was to correct me when I wrote that wrong concentration down. That was the only time I heard anybody's voice the whole class. All right, so let's assign you some problems and then I'm going to stop recording.
Raymond,
Yes.
I wanted to mention that Elizabeth sent a chat. That's
After I'm done recording.
okay.
All right. So, actually, I'm going to stop the recording now because I'm going to put this on YouTube. Nobody cares what problems we're doing.